once we get back to this, assuming we all got it reduced to this, the question was, I think we were looking at number 17. How many rows of A contain a pivot position? No. No. There are 3 pivot positions. 1, 2, 3. This is a pivot position. This is a pivot position. This is a pivot position.
So your X3 would be free?
X3 is free. Yes. Now, the question is, all right, there's 3 pivot positions. Does the equation AX equal B have a solution for each B in R4? Go back to this theorem. Back here that I told you was extremely important. Everything here is true or everything is false. You have to look back at your notes. Is this going to have a solution for every B that's in R4? What did that theorem say? How many pivots did that theorem say I needed? I need 1 in every row. Well, that means I would have to have 1, 2, 3, 4. I've only got 3. This is not an augmented matrix. Not once did I say augmented. Not once did they say augmented. This is a coefficient matrix. So you would be augmenting it with something out here, and it is possible to get 0 equal to whatever. So I needed 4 pivots here. So the answer is no. This does not have a solution for every B that's in R4. Okay?
So we pretty much, if we got it, when we do the reduction, if we got zeros all the way across one line, and we knew that's what the question
Yes.
that you could pretty much go ahead and say
You could
no.
stop.
You
Yes.
could stop working.
You could stop. Yes.
Okay.
Yes. In these matrices, you can stop until it answers the question. All right, there's another, problem 19 is related to matrix A also. And it says, can each vector in R4 be written as a linear combination of these columns in this matrix? And the second part of that, do the columns of A span R4? Think back to the theorem, you've got to know it. Okay, what did that theorem say? Like 4 different things are all equal to each other. And one of them had to do with the number of pivots. You had to have 4 pivots for everything to have a solution. You had to have 4 pivots for it to span R4. So question, do these columns span R4? No, you only have 3 pivots. You don't have enough pivots. All right, then the second part. Can each vector in R4 be written as a linear combination of these columns? Isn't that the same thing as saying, does it have a solution for every B in R4? Yes, it is the same thing as saying that, so the answer is no. Remember, if one thing is no, they're all no. Okay? Problem 21, let me ask you how you'd work it. Problem 21, let V1, V2, and V3 be those vectors. Does the set containing those 3 vectors span R4? Why or why not? And do you even need to work it? Think back to what we just said in answer to the question above this. If for these to span R4, I have to have 4 pivots. All right, if I've got 3 vectors, if they're going to span R3, I have to have 3 pivots. I've got 3 vectors, can the set that contains those 3 vectors, can it span all of R4? No. You have to have 4 vectors that are independent of each other to span R4. You've got to have 5 independent vectors to span R5. Okay, we haven't talked about dependent and independent yet, but it's leading up to that. You've got to have 5 pivots and a 5 by 5 to span all of R5. Is that making sense?
Right.
If you want to span all of R2, you've got to have 2 vectors and 2 pivots.
Well, I'm gonna say that even if you were to set that up, it'd only be a 3 by 4, and that tells you right there you've only got.
You're not going to have a pivot in every row. You
Right.
can't. The most you could have would be 3. All right, let's look at true false. Oh, wait, before we look at true false, sorry. I do need to just run through this last little bit of slides because it does have a comment in here that I think you see again on the true false. All right, this is going through here. This is their example 4. This is where they go through that, the other way to multiply that I showed you beside the definition, where you do row column. All right, if you're going to multiply A times X, the first thing is the definition. This is multiplied times the first column. X2 is multiplied times the second column. X3 is multiplied by the third column. You multiply and you add them together. That's the definition. The second way I showed you was row column. And what they want you to pay attention to is these are the rows that you get in your solution. The first entry on this product is the sum of products, sometimes called the dot product, using the first row of A and the entries in X. Oops. Using the first row and the entries in X. I showed you row column, remember? Row times column, row times column, row times column. Okay, now let's look at true false. Unless there's a question. So I have this feeling that y'all are like barely hanging on to this class. Like their fingernails sliding down the board or something. Am I right? Oh my goodness. Okay. True false. The equation AX equal B is referred to as a vector equation. False. Started off the first slide. Said it's a matrix equation. A vector B is a linear combination of the columns of matrix A if and only if the equation AX equal B has at least one solution. You got a 50-50 shot. Come on. Do what? Who said something? That's right. It's true. Thank you. All right, because that's what that theorem says. If you got at least one solution, then B can be written as a linear combination of the columns. All right, the equation AX equal B is consistent if the augmented equation A with B has a pivot position in every row. It's false. All right, this is talking about an augmented matrix. That theorem was talking about a matrix that was not augmented. It was talking about a coefficient matrix. If you've got a pivot position in every row, you might have one over here in this row, so it would be false. The first entry in the product, AX, is a sum of products. I just showed you this on that slide. The first entry is the sum of products. True. Yes, okay. I didn't know if I was dreaming that or not. All right, the columns of an m by n matrix A span Rm. Now, if the columns of an m by n matrix A span Rm, then the equation Ax equal b is consistent for each b in Rm. Thank you. If A is an m by n matrix, and if the equation Ax equal b is inconsistent for some b in Rm, then A cannot have a pivot position in every row. True. It is true. All right. Every matrix equation, Ax equal b, corresponds to a vector equation with the same solution set. Matrix equation and vector equations have the same solution set, yes. Any linear combination of vectors can always be written in the form A times X for a suitable matrix A and a vector X. True. At least you guys moving, huh? Thank you. Just come on. Solution set of a linear system whose augmented matrix is this is the same as the solution set of Ax equal b if A consists of A1, A2, and A3. Yes, true. If the equation Ax equal b is inconsistent, then B is not in the set spanned by the columns of A. True. If the augmented matrix A with B has a pivot position in every row, then the equation Ax equal b is inconsistent.
Oh.
Look at you. That's false. And last but not least, if A is an m by n matrix whose columns do not span Rm, then the equation Ax equal b is inconsistent for some b in Rm. Yes, true.